All right, so let's talk about BigCache. It's a .NET, I'm just kidding, it's a Go library. So my name is Mike Lloyd. For those of you that don't know me, I am Pivotal. I own Pivotal's technical relationship with Microsoft, which means that I do a lot of windowy things, and in my free time, I like to play around with Go. So when we talk about BigCache, we're really going to talk about four things. Who, right? So who works on the project, what the project is, why the project exists, and then how the project works internally and why you should care. So we are demoing the brand new template that was put out by the Golang guys at Google. So I have some feedback for them. If you see things that you like or want to change as far as like the way the template is presented, I'd love to hear about it so I can give that feedback to them and implement it in the PowerPoint report that I'm working on. So, section 1, who? So, the original owners and maintainers of this project are Thomas, Mattis, and Oleg. They work for a small retailer out of Europe called Allegro. They're similar to Amazon, right? It's an online retailer. And then myself, Mike, I am the project's first external contributor, first external maintainer. It was an awesome opportunity to kind of work with them and expand their reach into the community. Right? They had never had an external collaborator and contributor before. Cool. So, what is this project? So, BigCache is a fast, concurrent, and evicting in-memory cache that's designed to scale. And when I say scale, I'm talking hundreds of gigabytes with hundreds of millions, if not billions, of objects. It's literally designed for a top-level scale at the end of the day.
What does evicting mean when you're using it there?
So evicting is, think of it like an expiry token, right? So for example, when you drop an object into the cache, it will have a life cycle, and the eviction process is that life cycle.
Oh, okay.
Yep. So it's a way that you can basically evict items if you forget about them. Right? That way you're not always holding them in memory. So one of the big things we really wanted to focus on with this project was performance impact, right? So if we're holding hundreds of millions of objects in memory, how do we make sure that there's not a performance hit, right? And the performance is linear. So as we go through this project, a lot of our focus is performance, right? We believe performance is the ultimate requirement at the end of the day, and that anything that we implement in this project has to be highly performant, right? So speed is king and performance is God. So when I talk about performance being who we worship, this is not a joke. We are actually faster than the standard map in Go. So when concurrent maps were released in 1.9, I was really curious. I said, hey, I wonder if we're actually faster than concurrent maps. So I wrote a test with concurrent maps and added it to the project, and it turns out that we're generally 2 to 3 times faster than concurrent mapping. The reason is concurrent maps use atomic clocking, and we do not. So all of these tests are available in the project. I literally copied this to README, which I updated not too long ago. So one of the other things that we really believe in is testability, right? So before I joined the project, we had officially we had a 99.8% test surface, right? Everything that we possibly did was tested. I joined the project, and now it's at 90% of my tests. I'm just kidding. So there's just, as I went through and added things, there were some things that just couldn't really easily be tested in the way that code coverage tools believe they should be, and so it went down. But everything that we do has a test. Any new feature that we implement has a test. It's not necessarily test-driven development. Everybody writes their code a little bit differently, but everything is tested. So the other focus is simplicity, right? We wanted to make sure that this is very simple. It's very easy to use. It's very easy to consume. It's not difficult. There's not a high learning curve. Right? You don't want to learn something new. You just want to kind of be productive. So when I talk about keeping it simple, it's really easy, right? So initializing, there's a couple ways that we can provide some defaults, and then you're off to the races. If you're actually really curious about what the entire API surface is for this project, It's right here. Once you initialize the cache, this is the entire API surface. It is super simple, it's really short, and there's not a whole lot to learn. And that was one of the things that we really wanted to focus on, right? Keeping it simple and making it easy for everybody to use. So why would we go through this? Why would we want to make sure that this exists? So when the original creators wanted to go through and create and solve a performance problem that they had, what they really wanted was just a way that they could have a key value store with some type of REST interface in a way that was kind of easy to understand and easy to work with. So another aspect about this is that map, ultimately at the end of the day, is actually really slow. There are a lot of optimizations that you could do with map that would really increase the performance of it and make our project obsolete, but the Go authors want to make sure that things are generally kind of kept simple, especially for the standard library and standard language feature set. So some of those aspects is that map is slow. So another question that we actually kind of get from time to time on this project, especially when we go to promote it with friends, is, well, what's wrong with Redis? Redis is a key value store. It's really fast. It scales really well, and it's generally well documented as well as being really preferred by everybody. Redis is hosted by Azure, AWS, GCP probably has something. So there are a couple of reasons. One is the difference between an internal library versus an external solution. So with Redis, everything is external. So that means you need an SDK. It means you have to have a network round tripper and a whole bunch of other fun things. Whereas this is a library that you consume. It's local on your box, and it will grow as much based off the amount of memory that you have. And you can keep trying to go past your memory limit, but everything will crash. The other is latency versus load. A load operation on our end, which is basically a get, is nanosecond fast, whereas with something like Redis, there's network latency as you have to go transit to the Redis interface. And then we wrote a library, whereas Redis is a solution. It's a deployable Docker container, it's a deployable server, it's a deployable service, it's a whole lot of things that were more than just what the original authors were intending. All right, so let's talk a little bit about how this works and some of the ways that we are able to essentially be faster than the standard library, right? This is not actually a claim of being faster than math. So basically what we do is every entry that we get, we convert to a byte array because byte arrays aren't managed by the garbage collector. Not only that, but if we don't have pointers, right? So nothing that we do internally is a pointer. We don't, how do I want to phrase this? We don't do any serialization, right? Serialization is really, really slow generally, especially with the standard library. We do 0 serialization, which is awesome. Now, while I say that we do no serialization, we do hashing as well, right? So there is a hashing algorithm called Fowler no vol, and we use the 1A variant, where you can basically create a not cryptographically secure hash, but what's called an avalanche hash. So basically what this hash does is it hashes your data in a well-known format based off of a prime number that you select. And then what it allows you to do is every time you change anything that you hash, it gets avalanched. So an avalanche is when you change one small aspect of a hash and it gives you something so wildly different that it's essentially non-computable from point A to point B. The reason is because we support overwriting an object, right? So if you set object A in the cache, and then you want to go through and update object A in the cache, we use hashing in order to be able to overwrite without necessarily losing data. So as part of our no pointer option and our no garbage collector strategy, we store everything in memory in uint62 and uint32. So this is an optimization that was discovered in Go 1.5. In fact, this is the Golang issue if you guys are actually curious as to how that works. But not only do we not store pointers, but we actually convert everything to little endian binary after we've hashed it, just to make sure that every possible optimization is there, because like I said, we want this to be fast. We want it to make sure that you have a good experience. Cool. So we do have an HTTP server implementation. The reason the server implementation exists is because the majority of the people that went through and used this were like, hey, my use case is I need this for an HTTP server, or my package, that I want to that I want to store in memory, or whatever I'm storing in memory, needs to be accessible in other places. So I go and write an HTTP server. Cool. So my contribution to this project and why I'm their first maintainer is I wrote an HTTP server for them. So while it sounds self-serving, putting a quote by myself in here, ultimately this is for the project owners when they go to present it on their end, they have something useful. So one of the tenets of this project is everything that we do is from the standard library. We have no external dependencies whatsoever, both for the cache as well as the HTTP server. So this was built it's fully on the standard library, which is awesome, right? And it really helps when it comes to licensing and adoption of the project because, you can go to your boss and say, hey, I want to pull in this external project. Cool, what's the license? Apache 2. Well, what about its dependencies? There are no dependencies. It's the standard library. Cool, sweet. So the challenge was finding the right way to implement the HTTP server without any dependencies in a way that was both scalable and fast. So as part of that, when I went through and wrote this, I wanted to make sure that it was really, really easily extendable and very user-friendly. Right? Nobody wants to work on some just like disgusting web server that has this just weird middleware spider web of just disgustingness. And I was wondering about that. Anyways, so what I went through is I implemented what's called the adapter model. So basically what it is it allows you to go through and build an HTTP handler that does whatever you want to do. And then at the end of the day, right before we actually initialize the server, you can go through and loop through every adapter that you've created and then add them so that you can essentially build your middleware in a really easy and maintainable way. If you want to add authentication, it's really easily just build an authentication handler. It'll get added to every request. If you want to build a metrics system so you can kind of like go through and have stats, we can go through and implement that. If you want to have some other form of middleware, then you can go through and implement it really easily. Go through, implement a handler, boom, you're done. You can pick it up really, really easily. So the link at the bottom where it says the adopter model, that is, I can't claim credit for it because I didn't come up with it. It's a link to a Medium article that has a lot of great information on why this is a useful pattern and why it's sustainable and scalable and stuff like that. So some of the takeaways that you should have for this project as a whole is it's focused on productivity, right? We want to make sure that it's really, really easy for you to use. We want to make sure that it's blazingly fast. This should be the fastest cache solution that you ever use. If it's not the fastest, you should come talk to me and I'll make sure it's the fastest. And then it's black box. You shouldn't care how it works behind the scenes other than it's fast and it's easy. Right? So we don't want you to care about the hashing. We don't want you to care about the sharding or anything else that we do behind the scenes. It should just work and it should be fast. And that is the end of it. So that's generally what the new template looks like. It's really nice. It could use a little bit of work to be a little better, but for the most part, it's not bad.